All right, this is Physics 1C, Hour 3 for April 22nd. So we are going to continue talking about the magnetic force on a loop of wire. We just figured out that the torque on this wire, when it's oriented horizontal, is going to be clockwise. And this is the value that we get, the current times the area of the loop multiplied by the magnetic field. And so now what we'd like to do is to say, well, okay, if the torque is clockwise and it's being has a fixed axis that's running through the center like this, then after some period of time has passed, the wire is going to be oriented so that the bottom edge is going to be kind of like this. Okay. And we'd like to now be able to calculate what the torque is in this new scenario, right? So let's do that. So now there's an angle theta that is made with the magnetic field, and a new vector has been drawn here. And this vector is the area vector for the loop. Remember that what we learned when we were talking about electric flux is that an area vector always points perpendicular to the area of the object. And really there's two possibilities for what way that could point, right? One would be this direction. What would be another vector that would be an area vector that would be perpendicular to the loop?
Pointing down?
Out of the screen.
Down to the left. Can anyone guess why it's pointing up and to the right instead of down and to the left? Any ideas?
It's turning clockwise.
What's turning clockwise? Oh, because the whole loop is going clockwise. That's kind of part of it, actually. Anyone else might be able to guess? It's related to the right-hand rule, if that helps at all.
For the
cross product of the like the L vector and B.
maybe it has to do with the current.
It does have to do with the current, yes. So you're kind of right, Kenny.
Yeah, like the current's traveling in the direction of the loop, let's say.
Mm-hmm. So the current's doing this, right? I don't know if you can see this very well, but it's coming out, and then it's going this way, and then it's going back in. So the current is going in a way that's like this, right?
Yeah.
So now if you take your thumb and you point it in the direction of that area vector, would you all agree that the direction that your fingers move is basically like sweeping the current along? You have to use your right hand, right? Point your thumb along that axis where the A is, like that right there, and then let your fingers sweep. They like kind of push the current along, basically, right? So that's how you define what the area vector is. Okay? When we were doing magnetic flux, we just said the area vector goes out, right? But when you have a loop, you need to say that the direction of the current is going to determine the direction of your area vector. And so when the current goes around like this, the area vector goes this way. If we reverse the current, the area vector goes this way, okay? Does that make sense? All right. So, we got our new thing called the area vector. That area vector makes an angle of theta with the magnetic fields, and that same angle theta is going to show up here at the top. And if that's not super obvious, it's because this angle here needs to be 90 minus theta, because that's a right angle. And so if you do 180 degrees, so theta plus 90 plus this should be equal to 180, which means that this little red angle down here has to be 90 minus theta, which means that because this is a right angle over here, that this is also theta. Okay, you can convince yourself of that. You're all quite capable of doing that, I'm sure. Okay, so now what's the torque? Well, now the net torque is going to be equal to, the torque over here is going to be force times the distance to the axis, which is again b over 2. And now there's really two options of how you can do this. And what I'm going to do is use the lever arm method, okay? If I extend my force back this way, then the perpendicular distance to the axis is between here and here. And the lever arm then is b over 2 times the sine of theta. Because theta is this side, b over 2 is the hypotenuse, so b over 2 sine theta, this thing is what we would call the lever arm, right? So that's the torque on side 2, and the torque on side 4 is going to be exactly the same. It's going to be F4 times B over 2, also times the sine of the same angle. Because you should probably be able to see that if this distance between this point and the axis is B over 2 sine theta, you can draw the exact same thing so that this distance is B over 2 sine theta between here and here, right? Should be the exact same distance, basically, right? Because this angle is also theta. Okay, I'm going to erase all the stuff I just wrote, but I just want to keep the picture kind of neat. So that's our torque now. And now if we plug in what F2 and F4 were, if we scroll up a little bit here, so F2 was IAB, right? And F4 is the same, IAB, because sine 90 is 1. So what we get is that our net torque is, this was I times A times B multiplied by B over 2 sine theta. And F4 is exactly the same, I times A times B over 2 times the sine of theta. And I guess one thing that I should say is that even though these things have rotated, right, has the angle between the current flowing here, remember this is current, right? The dot represents the current coming out, and then it flows down this way, and then it goes back in here. Has the angle between that current right here and the magnetic field changed? Or is it still 90 degrees? Current out, magnetic field this way, it's still 90, right? Mm-hmm. Okay, so we didn't need to change what we got here. Okay. The only thing that's new is we've got this sine theta thing hanging around. So the final answer we get then, when we add these two together, is I, again, times A times B, because we do B over 2 plus B over 2 and you get B, times the magnetic field, times the sine of the angle theta. Now what is theta? Theta is the angle between the area vector and B now, okay? So theta now represents the angle between A, area vector, and B. Because A times B is once again the area. So now we have I times A times B times the sine of theta, and we're almost to our final answer now, but we are going to manipulate this a little bit because we're going to define a new quantity. So in order to do this, what we want to say is, let's take this piece right here, okay? In fact, I want to make one other statement right here. So this would be the answer if there was exactly one loop of wire. But one of the things you can do with wires is you can basically just wrap loop after loop after loop after loop. So we started with just one loop that was a rectangle, right? That's one loop, right? But there's nothing stopping us from just continuing to wind loop after loop of wire on top of it, okay? With exactly the same dimensions of A by B. We can just have multiple loops, okay? And they can all be connected, right? Because all you need to do is you just take a wire and you keep wrapping it around and around and around and around and around and form it into the shape, right? Because, you know, if it's a copper wire, for example, it's going to have some rigidity to it. So it's very easy to form it into this shape and to control what the shape is, right? You can make the area bigger if you wanted to. What would happen to the torque if we make the area bigger, but we keep the current and the magnetic field the same? What would happen to the torque?
It would increase.
And go up, right? So if you wanted to increase this effect, what would you do? You'd increase the current, you'd increase the size of the loop, you'd increase the magnetic field. All of these things would increase the torque that's felt right here, right? But in addition to that, an even simpler way of increasing the torque would be to just say, suppose I take in loops of wire. If I have in loops of wire, each one of them is going to feel the same torque, basically. Each one of them is going to feel IAB sine theta. So I have 2 loops. The torque would be 2 IAB sine theta. If I have 10 loops, it would be 10 times I times A times B times sine theta, right? So if I have in loops of wire, then my torque is going to end up being N times I times A times B, and we still have this sine theta thing sticking around right here. Right? So, now that we have all of that, what I'd like to do is to take all of this here, and I gotta do one more step actually. The next thing to do is to say, let's replace this with N, I, A. Let's get rid of our sine theta thing here, because we know that if we write A cross B, that's going to give us a sine theta, because remember that the angle between A and B was theta. So if I do A cross B, that's going to give me AB sine theta, right? And it'll also give me the right direction for the torque. Remember that torque in this case was clockwise, right? If I go A, which is this way, cross B, my thumb points into the page, which is clockwise torque, okay? This torque in every case basically is clockwise. Clockwise and clockwise right here. So A cross B naturally gives me that, right? Can you all see that? That A cross B, not only does it reproduce the sine angle here, but it also gives me the right direction for the torque. So what we'll do then is we're going to say take this piece in the front, okay? And we're going to say let mu, which is a new vector, be equal to the number of turns in the loop. By the way, this is for n loops of wire. We're going to call this magnetic moment. Mu is going to be equal to n times the current multiplied by the area vector. We call this magnetic moment. And then we can just say, well, now our torque, which I can now write as a vector, can be written much more simply as just the magnetic moment cross product with the magnetic field. And that is our final result. The size of the magnetic moment is dependent upon the current. The bigger the current, the bigger the magnetic moment, the number of loops, and the area. And altogether, that gives us this. The torque is just magnetic moment cross product with the magnetic field.
Wow, so you could create a lot of torque with just as many loops as you want.
That's exactly right. And that's exactly what people do when they're designing electric motors. You just put a whole bunch of loops of wire in there. Now, what happens in my system right here over time? So I'm going to draw on here that this is the direction of the magnetic moment, mu. Okay? So basically, if I have any loop of wire, and it carries a current I, like this, then I can say if I sweep my fingers in the direction of the current, the magnetic moment is going to point in the direction my thumb points. So in this case, if I have a loop of wire like this, the magnetic moment vector is going to point this way. Okay? All right. Now, when I have this magnetic moment vector, I can kind of predict what my loop of wire is going to do. Okay? And what's going to happen is that there's going to be a torque, and that torque is going to have the effect of kind of turning the loop towards the direction of the magnetic field. What happens to the torque when this wire is straight up and down? What I mean by that is, in that same scenario right there, what happens to my torque here if my wire is like this? So this was my current coming out, that was my current going in. My magnetic moment would point this way, and the magnetic field that's external is also pointing in the same direction, B. What happens to the torque now? No torque. And if you can't see it, let's just draw the forces on here. What's the direction of F2? Well, before F2 was up, and this is the same direction now, that doesn't change. And what direction is F4?
Yeah.
Yeah. So now, zero torque, right? Because the angle between mu and B is equal to what? 0. Yeah. So So if the angle is 0, then there is no torque, right? What would happen to the direction of the torque if it rotated just a, if we now naturally this is like an equilibrium position, right? This is an equilibrium position. So imagine that I take a loop of wire and I orient it like this with no current in it. I turn on the current. What happens? It's going to rotate to this position, right? And once it's in this position, there will no longer be any energy left to rotate it. No longer be any force left to rotate it, right? So this is a type of equilibrium position. What would happen if I continued to rotate this? Now I'd have to do this physically by hand. I come in here and I exert a force on my object here. I take my loop and I push it to the right. What's the direction of the torque going to be now?
To the left?
It's going to torque back the opposite way, right? Maybe I should draw it just so it's clear. So if we're in this position, let's use the same colors. If we're in this position here, where there's my current coming up, my force is up this way on the top, and here's my current here, the force is still down this way. And what's the direction of my magnetic moment now? Well, based on the current, it's going this way. And my magnetic field vector is still here. Oh, that didn't switch, did it? I want to go green. Green. Magnetic field's still this way. That is theta now. What's the direction of the torque? Is it still clockwise?
Be counterclockwise.
Counterclockwise, because now it's going to rotate that way and it's going to rotate this way, right? So the direction of the torque now is it's switched. Up until we got to, so here, torque was clockwise in this picture. We got to here, 0 torque. And then as soon as we cross past the equilibrium position, the torque reverts back the other way. Because after all, it's an equilibrium position. Just like a pendulum, right? A pendulum, if you displace it a little bit from equilibrium, equilibrium is straight up and down, it goes right back to equilibrium, right? Eventually. You push it to the right, it goes left. You push it to the left, it goes right. I don't know if those directions are switched for you as you're looking at this. But you understand what I mean? Like, it's an equilibrium position. So it's just going to naturally revert to that position no matter where you... So what does this mean about mu and b? Well, it means that if I have an object that has a current flowing in it, and I put it into a magnetic field, it's going to kind of tend to make it so that mu and b want to line up with each other, right? Does that make sense? So mu is going to naturally tend to point in the same direction as the magnetic field. Does that make sense? So mu tends to align with the magnetic field.
So that's where there's like least potential.
Exactly, right. And your book talks about potential energy and stuff like that, and you can look at that if you want to. But yeah, there's no energy here anymore, basically. Whereas we had the maximum energy you could possibly have when it was oriented like this, because mu really wants to line up, right? See, mu wants to go from here down to here. It wants to rotate down to B. And does that remind you of anything? It should, because if you think about a compass, this is exactly how a compass works, right? So think about this. A compass needle has like a north end, right? And it's got a south end. This is like the north end right here. And this is the south end. And if I take that compass needle and I put it into a magnetic field that points this way, what's it going to do?
Rotate until it points that way.
Yeah, the compass needle is going to rotate until it lines up with the magnetic field. So it turns out that a compass is like has its own little magnetic moment, and it points this way, right? And the compass needle is just going to rotate until it points in the same direction as the magnetic field. So it turns out that not only does a compass do that, but also a loop of wire does exactly the same thing. It does exactly the same thing. It acts just like a little compass needle, and it wants to line up with the magnetic field. That's pretty amazing, right? that a compass needle and a loop of wire that carries current are quite literally like the exact same things in terms of how they interact with magnetic fields? That's pretty amazing. That a compass needle is the same thing as a loop of wire from a certain perspective. So that's what magnetic moment is. And this is kind of related to the question you asked earlier, Cam, about the G-2 experiment. Because they're actually measuring something that is related to the magnetic moment of the muon, because it turns out that it's not just loops of wire that have magnetic moments, right? Because take, for example, really any atom, okay? Take any atom. Take an electron, take a neutron, doesn't matter. An atom, like a hydrogen atom, for example, that has a positively charged nucleus with an electron that's orbiting around in a circle like this. So you've got an electron that orbits like this, right? A single electron orbiting around. Well, an electron that orbits around like that is the same thing as a current that flows the other direction, right? Because it's a negatively charged particle going this way, so that's the same as a current flowing this way. And if I have a current flowing around a loop like this, and I left a detail out, which is that magnetic moment is N times I times A, and we derived this area for a rectangular loop, but it doesn't matter if it's shaped like a rectangle now, because it's just area, okay? It can be shaped like a circle, it can be shaped like a square, it does not matter. All we care about is the area of the loop itself, okay? Which is kind of nice, so that we don't have to always make things into rectangular loops. We can instead make things into circles, because I believe circles are a much more efficient usage of the circumference to the area, or the radius to the area, right? Isn't that right? If you want to maximize the area compared to the circumference, don't you want to use a circle? Did I get that right?
I think that's actually minimum.
Is it the minimum area?
I think it's the minimum. Because, yeah.
Okay, let's come back to that. But the point is, we can talk about that after class, I guess. All right, so the point is that it doesn't matter what shape it is, right? Okay, so we've got a loop now, which is basically just an electron that's moving around, which is the smallest kind of current you could even possibly have. What direction would the magnetic moment for this object point?
Be downwards.
Yeah. You sweep your fingers in the direction of the current. It's sweeping around like this. Your thumb goes down. So our magnetic moment vector now is pointing straight down. So a hydrogen atom has a magnetic moment. And if you were to place a bunch of hydrogen atoms into a magnetic field, let's say you place them into a magnetic field that goes like this, then they're going to want to twist so that their magnetic field points and lines up with that so that their magnetic moment lines up with that magnetic field. And not only do atoms have magnetic moments, but electrons have magnetic moments. Neutrons have magnetic moments. Protons have magnetic moments. Everything that has charge of some kind has a magnetic moment. And it's one of the ways that we can investigate the properties of the particle is by seeing kind of how these things align up with magnetic fields. And that's what they're doing in the muon experiment. And I may talk more about that after class, after we've done a couple of problems here. But, yeah. So, let's solve some problems with this. All right, we're right at the cusp of kind of seeing how electricity and magnetism are connected with each other now, right? Because we've introduced this idea of magnetic fields, and now we've figured out that it turns out that loops of wires have this effect where they tend to interact with magnetic fields. And the next step that we're going to see next week is that not only does this object have a magnetic moment, but a loop of wire actually creates its own magnetic field that points exactly in the same direction, as it turns out. So not only is there a magnetic moment there, but there's actually a magnetic field that this wire produces itself. And it turns out that it points exactly in the same direction. It's going to point straight up. And it's going to be equal to mu naught times I over b. We'll see that. Anyway, so we want to do some problems now, so we can look at the applications of these things so that you can kind of hopefully solve some problems. Alright, so this is the problem we're going to look at. I believe we're going to, if we have time, we're going to try to do another problem from another textbook that I didn't copy on here yet. So, magnetic torque on a circular coil. So we have a circular coil which is 0.05 meters in radius with 30 turns of wire. So now you're going to start seeing this show up a lot. Just all of a sudden you're going to start seeing turns show up. This is your, this is coming from here. Okay, let me grab these two equations. Come on. Control paste. All right, there we go. So this number of turns, right? You're going to see this show up a lot. Every time you see the word turn, they mean loop. Basically, it's like 1 turn, 2 turn, 3 turn. It lies on a horizontal plane, and it carries a counterclockwise, as viewed from above, current of 5 amps. The coil is in a uniform 1.2 Tesla magnetic field directed towards the right. So our magnetic field now is going to the right, and it's kind of in the plane of the coil. The coil, yeah. Find the magnitude of the magnetic moment and the torque on the coil. Okay. So our magnetic moment, as we can see above, is equal to the number of turns, which is 30 turns. Turns doesn't have a unit, I'm just writing it. Current I is 5 amps. And the area, well, we know the radius, so it's a circle, so we'll do pi times the radius squared, which is 0.05 meters squared. And that'll give us the magnitude of the magnetic moment. So for me, that's 30 times 5 times pi times 0.05 to the 2. Whoops, times 0.05. I get 1.18.
Me too.
Okay. 1.18. And then what are the units? Well, it's just amps times meter squared. That's our magnetic moment. Then we want to find the torque. That's easy. Torque is mu times b times the sine of the angle between them. In this case, what's the angle between mu, which goes up, and b, which goes to the right?
90.
90. So we do sine 90. So then this is going to be equal to 1.18 amp meter squared multiplied by b, which is 1.2 Tesla. They love using this number for some reason, 1.2 Tesla. So I think we're going to get an answer that's something like 1.40 or something like that. Torque, newtons times meters.
I got 1.42.
42, that sounds right. Okay. I knew it had to be less than 1.44 because this is basically 1.2 times 1.2, which is 12 times 12, which is 144. But 1.42. And yeah, there's our answer. That's the torque. Oops. That is the torque. Okay. How much time we got? 4:40. Do we want to do this harder version? I think we do, because I know it's on your homework. And we in the right book? I think we are. All right, where is this problem? We can do this one. This is a good one. I think this is what we want to do, but I'm just going to look real quick and make sure it's not something else. Okay, so this is going to take 2 screenshots to get it. Alright, we're going to print screen here, go over to paint, and we'll grab this question. And then I'm going to grab the picture. 29.47, which should be like right on the next page here, is this one. So grab this one. I'll include the name. Okay. I don't know if you've all started doing your homework yet, but there is a problem that is almost exactly like this on your homework, and it always gives people a lot of troubles. So I think we should do one and make sure everybody can understand what's happening. Okay, so we have a rectangular coil. It consists of n equal to 100, closely wrapped, there's that word again, turns. It just means loops. And has dimensions of 0.4 meters by 0.3 meters. So 0.4 on the side, 0.3 on the side. The coil is hinged along the y-axis, so it is made to rotate basically along this axis right here. And its plane makes an angle of 30 degrees with the y-axis. So that's this angle here. Start with the x-axis. What is the magnitude of the torque exerted on the coil by a uniform magnetic field of 0.8 Tesla directed along the positive x direction? So we're going to have, oh, it's drawn right there, B. Now B is going to be uniform. It basically is going to be everywhere in the xy plane. So B is, you know, everywhere here in a straight line this way. Okay, so everywhere in the xy plane we have a magnetic field B, and then of course extending out in the positive z and negative z direction. Just imagine a uniform vector field that's pointing to the right everywhere you are in the entire coordinate system here. Okay, so the way you could write that in terms of a vector would just be B is equal to, what's the value? 0.8 Tesla times I hat. Everywhere. No matter where you are, that magnetic field is there. The current in the wire is 1.2 amps. And we've got A and B right here. Question A is, what is the magnitude of the torque exerted on the coil by this field? And then question B, what is the expected direction of the rotation of the coil? So we need to find basically the size of the torque as well as the magnitude of the torque. Okay. Now, I think the way this picture is drawn, it is very difficult because of the three-dimensional nature of this to understand how to solve this problem. And so what I like to do for this type of problem is to draw a new coordinate system that is oriented like this. So what I'm going to do is we're going to flip it so that this is going to be the positive z direction now. This is the positive x direction. So then we're going to basically take our coordinate system so that positive y is coming out in this direction here. So I'm just going to put a little line right here and say this is the plus y direction right here. Okay. Now my coil is going to be oriented. Whoops. My coil is going to be oriented like this. Make it black. With the current, we use red for the current, is going to be flowing this way. And then that current is going to flow in on this side, and it's going to come back around, and it's going to be flowing along the positive x-axis coming out this way, or positive y-axis coming out this way. Can everyone see how this picture is the same as the picture here? But now we're basically looking at it in this direction. We're looking at it in that direction.
Yeah, that looks clear.
Okay. So this will help you when you're doing your homework on this particular problem. I would highly recommend just doing this because it's going to make it way easier to figure out what's going on. Okay, so can you all tell me what is the direction of the magnetic moment for this loop now?
Southwest.
Wrong.
What? Oh, okay.
No, northeast.
Opposite.
Yeah, it's northeast. Yeah, it's only southwest or northeast. So 50-50, you can kind of just guess. But it's the current again. It's flowing around like this. I don't know what you can see. The current's flowing this way. Sweep your hand in the direction of the current like you're pushing it along, and then your thumb is going to point in the direction of the magnetic moment. So let's draw that vector on here. Something like that, right? Now let's draw B on here. Where B is basically pointing in this direction, right? So that would be the angle between the two of them, yeah? Go ahead and call it theta. Now let's answer part B first, because I think you all can figure this out. What is the direction of the torque? Is it going to want to rotate this way, or is it going to want to rotate that way? Clockwise or counterclockwise? And if you're not sure, remember what the magnetic moment does. Let's go back just real quick and let's look at what we said. if I start with a system like this, where the magnetic moment is pointing up and to the right, over time, what's going to happen to the magnetic moment? It's going to want to line up, right?
Clockwise.
It's going to want to line up, right? Yes, the answer is clockwise. Because here, our magnetic moment vector is up and to the right, and B is to the right. So that magnetic moment vector basically wants to swing down until mu, which is starting off this way, is going to line up with B, which is going this way, right? Can everyone see that?
Yeah.
So the answer is that it's going to rotate clockwise. So part B, the answer would be, this picture, how are you going to say? It's going to rotate until it lines up with the z-axis, basically, right? It's going to rotate down this way. So we're going to call that clockwise based on our picture. That's part B. Now there is a way to define clockwise torque using I hat, J hat stuff, right? And I'm pretty sure this shows up on your homework. So can anyone tell me, how do I define the direction of the torque if I want to say that it's clockwise? Does anyone remember how it's done? If the answer is going to be positive J hat or negative J hat. Does anyone know?
Clockwise.
Now we know it's negative J hat. Negative J hat. And the way you can figure that out is that in order to make this thing rotate clockwise, like this, right? I stick my thumb on the negative y direction, and then what does my hand do? It rotates clockwise, right? If I wanted to rotate counterclockwise, I would point my thumb in the positive y direction, and that would be counterclockwise. Does that make sense?
You could also just do it by like doing right hand roll for U cross B, right?
Yeah, absolutely. 100%, yeah. Mu, B, negative J. Yeah, that's a very good point. Absolutely, you can do that. 100%. Okay, now that we figured all that stuff out, that's the hard part. Now we just crunch some numbers, because these equations are really easy to use. The hard part is mentally visualizing the way that things rotate, looking at things in 3 dimensions, redrawing things so that you can understand them better. I just highly encourage you, when you're doing any types of problems that involve 3 dimensions, is to redraw it in a way that you can understand. However that happens to be, everybody's different. So just redraw it in a way that's easier to understand when it's in 3 dimensions. Try to maybe draw it in 2 dimensions if you possibly can. This is just one example of how you can do that. But it's always helpful to just kind of redraw things in a certain way. Okay, what does part A say? What is the magnitude of the torque exerted by the coil on a uniform magnetic field? So we know that the torque was equal to mu cross B, right? And we know that mu is number of turns times the current times the area multiplied by the magnetic field, B. And then when we do a cross product, we get a sine theta. And we've already figured out what the direction of the torque is right here. So we'll just turn this into a, we'll find the magnitude of the torque. So how many turns? 100. Again, no units on this. What's the current? 1.2 amps. What's the area? Well, it's a rectangle, so 0.4 times 0.3. And times B, which is 0.8 Tesla, I believe. Sine of the angle. Now this is another thing that's going to be kind of tricky. I was a little sloppy here. I said I called this angle theta. That's kind of a lie, because this is theta right here, right? Which means what I'm going to do is I'm going to call the angle up here in this triangle here phi, because I know that the magnetic moment vector makes a right angle with the loop. So what I can do then is say this angle is also phi, and since theta was 30, what does phi need to be?
60.
60. And so that's the angle that we're going to want to use in here, 60 degrees. Be really careful about that kind of stuff with these problems, because it's really tempting with any problem where they just give you an angle to just be like, I just use the angle. Just got to be kind of careful. And then we can calculate all of that. And what we get
I got 9.98.
Perfect,
I got
thank you.
the same too.
I'm almost certain that's the answer because I can remember doing this problem for 10 years now or something. So you get 9.98 torque, Newton meters. You can figure out for yourself that amps times meter squared times Tesla gives you Newton meters because Tesla is Newton meter over amp. And you're multiplying by amp meter squared. Amp meter squared. You multiply those out, you get amps cancel. No. Newton per meter amp. So one of the meters cancels, the amps cancel, and you're left with just Newton meters. Okay, so that is our torque. And again, we figured out that it was the negative j direction, so the proper way to write this would be negative j hat, just like this. And that is our answer. Complete answer for A and B. Okay, I'm almost certain you have a homework problem that's exactly like this. Does anyone have any questions? Okay, so the last thing that I want to do, in a way, I guess we can almost do this next week because we're really running close to the end here. I want to watch this video. It's kind of long, though. So we learned that by taking a loop and placing it in a magnetic field, there's going to be a torque, and that torque will tend to align the magnetic moment with the magnetic field, right? But what if you want to make a loop just continue to rotate over and over and over again in a circle? The method that we've described here isn't exactly going to work. However, if we can change the direction of the current, right, so that when it got to this position right here, if we flip the direction of the current, right, then exactly at this point, what will happen is that we can actually make this loop rotate in a circle. Every 180 degrees, if we flip the direction of the current, we can basically make it rotate over and over and over and over again. Okay? And that's what we call an electric motor. That's what an electric motor is. It's something where you feed electricity in, there's a magnet inside of it that makes it so that the loop just continues to rotate, so that you can directly convert from electricity into mechanical motion, from electrical energy into mechanical energy, so that you can use electricity to make things move. And that's how an electric car works. That's how any kind of electric motor works. And it's generally pretty hard to draw how this works. There are pictures in your textbook of what I'm describing, and I am just not even remotely good at drawing these type of pictures. So the direct current motor, here we go. Here we go. We're going to look at these pictures, and then we're going to watch a video. Okay. This is the basic idea. We take a north magnet, a south magnet. We place within them a loop of wire. So here is our loop of wire. Can you see what direction the magnetic moment vector is? It's right there. It's that orange line. It's pointing down, right? Magnetic field is here. So what's going to happen? The loop is going to want to rotate until mu points in the same direction as the magnetic field, right? It will do that right here. But then something weird happens. Down here we have a battery. The battery is connected with wires. The current is going to flow into the red side over here. And then it's going to flow out the blue side over to here. But notice the way that there's a connection made here. So the wire is making contact with this little loop thing called a commutator. And you can see the red side of the commutator, you can see the blue side of the commutator, right? But notice that right in the middle, there's a gap at the top, and there's a gap at the bottom. The effect of that means that when we get to the perpendicular position right here, where the blue piece is rotated up and the red piece is rotated down, there is no longer any current that's flowing because of the gaps right here and right here. And what that means is whatever momentum, whatever angular momentum that this object has picked up due to rotating, it's just going to continue to rotate in that same direction. And what happens is that after it rotates past that point, contacts are made again, and the current that was flowing in the red side over here is now flowing in the blue side over here. So kind of red and blue have switched each other, right? But that means that the magnetic moment is down again, which means that it can rotate back up to the same position again, and then repeat the process over and over and over again. Again, transferring the electrical energy of the battery into the rotation of this object, and then if you stick something on the end here, you can basically have rotational motion and use it to drive a little car or something like that. Now, like I said, did any of that make any sense? Did you all follow? Go ahead.
What's keeping the thing rotating is the commutator?
Right.
The gap between the...
Right. Because it switches the direction of the current every 180 degrees. So the current's... It's not really switching the direction, it's just switching which arm it's traveling down, basically, right? And that just makes it so that you can just keep rotating and rotating and rotating. So let's watch this video. It's really long. If you all need to go, you can just watch this video yourself later. I have it linked on on Canvas, but I'm just going to start it, and then I'll stick around at the end. We can talk about stuff. But oh, wait a minute. Is this one shorter, or is it the same? Is it the same one? That's the same one. Well, anyway, I'm going to share. We'll switch screens, and then we'll look at this. And again, if you need to go ahead and go. But if you want to watch this video, it's not bad. It's a pretty good animation of what happens. Sound working okay?
Yep.
I just wanted to mention, by the way, this is normally what happens when we're doing these physics demos with this this thing, is that it rotates and it just gets stuck basically in one position when it lines up right on those edges. So it's kind of interesting that you mentioned that. So first, the we don't need to watch the advertisement. All right, what did you all think of that video? Did that help you understand what's going on?
It's pretty good.
Yeah, it's pretty cool.
Cool. So there's definitely some topics that he brought up there that were kind of new, but we're going to be talking about them next week, so it's, I think, a pretty good way to introduce it. And, we already said that that this loop, basically, not only does it have a magnetic moment, but it literally acts like a magnet, right? I said that it's acting just like a compass would, right? So, him saying that the loop acts like an electromagnet is the same thing as saying it has a magnetic moment. They're completely interchangeable concepts, right? So, but yeah. Anyway, so that's how a motor works. We're definitely out of time. We went a lot longer today because this is a pretty thick chapter in your textbook, and I want to make sure we cover all our bases. And yeah. Anyway, anyone have any questions or comments? All right. If not, I hope you all have a good weekend.